So hi everyone, my name is Chris Alton. So I'm from the Swansea University and I'm also the director of Oriel Science. And where I am now is actually in Oriel Science. It's a science exhibition centre in the centre of Swansea. If you know Swansea, it's on Castle Street. So basically that way is Castle Square and that way is the train station. We've got a website, orielscience.co.uk. But more about Oriel Science later on. My job today is to bring physics, particle physics in particular, and sports science together. Okay, it's a tough task, but someone's got to do it, and why not me? Okay, so let me show you what we're going to be doing, and I've got this little PowerPoint, and here we go. Okay. So in that picture there are lots of particles interacting. Okay, and it turns out that there is a sports science, sports fan kind of angle to that, which I'm going to describe. Yes, really I am. Okay, so here's the kind of traditional pictures of particle physics that you might have seen before. These are all part of the Large Hadron Collider, which is a machine in CERN. That's the laboratory called CERN. It's just near Geneva. And the image below is, in fact, like a camera. It's like a photograph of the particles colliding. Okay, so our task in the next little bit of time is to understand how those particles interact using a sports analogy. So for those of you who have got a keen ear for accents, I've spoken perhaps long enough to perhaps you to work out where I'm from. Obviously, normally, in normal times, I'd be giving this live and I could see your faces and there'd be some sort of interaction and people would shout out where I'm from. People shout out New Zealand quite often. That's wrong. Some people shout out South Africa. That's also wrong. I'm actually Australian, okay? So Australians, like many nationalities, love their sport. So here is some sport. Okay, you may know that the sport Australian rules football is played, you guessed it, in Australia and not many other places. Okay, so imagine now that you're trying to understand Aussie rules football. So let me just play a bit of a clip. Okay, so here is, I think it's Collingwood versus Adelaide, okay? Two teams. It's probably played in the MCG, the Melbourne Cricket Ground. It seems to be random people doing random things, and every now and then they stop for no apparent reason. The guy who caught the ball kicks it, and there's the goal. It's not a rectangle, it's not rugby posts, it's 4 vertical posts, 2 tall ones and 2 shorter ones. A guy dressed as a butcher does funny things with his hands, and it seems that there are not very many rules. Watch this knee in the back of the head. Okay, that's perfectly reasonable. And that, the commentary says, is one of the best marks that season. Okay, that's legal. Okay, so how is this possible? Okay, what's going on here? Well, imagine that you are going to Australia studying Aussie rules football. Okay, so your task is to see this crazy sport, and it appears there's no rules. So the middle word there is rules, but it appears at first there's no rules. But imagine though you were very keen and you went to the MCG for not one match, but many matches through the season. And after a while, you would see that at first it seems chaotic, but in fact, after a while, you could kind of predict what the umpire was going to do in certain circumstances. Okay, so you'd see 18 people on each side. The field is an oval shape. It's not a rectangle. There seems to be no offside rule. It seems that you can never be sent off. Okay, all those things are true. Okay, but there are some rules nevertheless. And if you were to watch enough Aussie rules football matches, you would actually understand what those rules were. And you could laboriously study enough videotapes, go to enough matches, and write down the rules. Okay, and then eventually you'd end up with your prediction of the rules of Australian rules football. And then if you were to compare it with the actual true rules book, okay, you would find that the two agree. Okay, so that's the sporting analogy. So particle physicists are seeing these really weird interactions. At first it seems chaotic, at first it seems there's no rules at all. But when we study it long enough, we'll see that certain patterns happen. Okay, if one thing happens one time, there is a chance that the same thing will happen another time. Okay, so there's certain patterns, underlying features of the way that particle physics interacts. And particle physicists are like you going to MCG trying to discover the rules of Aussie Rules football. Okay, particle physicists are going to CERN to study not the rules of a sport, but the rules of Mother Nature. And so what's going on is when we study that, eventually we'll end up with the patterns, and then we'll get the rule book, not of sport, but the rule book of nature. Okay, so studying sport and studying particle physics in a weird kind of a way are related. Okay, so how do we go about studying particle physics? Well, let's take you on a brief kind of chemistry and history lesson. The thing on the top left is quite a small thing, okay? It's a molecule, far too small for the human eye to see, okay? There would be millions of those, billions of those across a millimeter, okay? That's the molecule. It's a kind of cartoon, a diagram, a drawing, a representation of water, H2O, okay? Now, what's inside a molecule, and that's what the ancient Greeks wanted to ask, what's the smallest thing which makes up all particles? Well, smaller than the molecule are atoms. So the H is an atom and the O is an atom. Okay, so the top right, you've got an atom. Okay, it's a very stylized, kind of incorrect picture of an atom. And it turns out that through chemistry, and Mendeleev, a Russian chemist in the 1800s, they worked out that every single atom that is known to humans can be put on that table, on that diagram. Okay, there aren't any atoms that exist that are not there. Okay, and furthermore, those atoms come in patterns. They naturally fit into rows and to columns, and things in the same columns have got similar chemical properties. And so that's the periodic table of chemistry. That is, if you like, in a sense, you know, the numbers of plays in a sporting field that you could take. Okay, you've got to pick amongst those to send out onto the field to do your chemistry for you. So that's the periodic table of chemistry. Now, the atom there, you can see the way it's drawn, it's quite clearly made up of smaller things. And so particle physics studies what's inside atoms. And of course, there's two layers deep on that. In the middle of the atom is a nucleus. Okay, but inside the nucleus, there's things called protons and neutrons. And you guessed it, inside protons and neutrons, there's quarks. Okay, so quarks are the smallest thing that particle physicists know exist. Whether they're things inside quarks which make up quarks, we don't know. There's no evidence that there are things which are smaller, but all the historical insight we've had suggests that just as when we think we've got the smallest thing, just when we think we've arrived at the ancient Greeks' kind of final answer, what is the fundamental unit which makes up all matter, every time we thought we got to the end of the road, there's actually more things to travel. Okay, so, you know, I wouldn't bet either way whether quarks are fundamental or not. Okay, so here's the thing about quarks. Quarks have got their own kind of periodic table. In the top right, hopefully you can kind of see, there is a table as well. Okay, so that's a photograph I took. It's a beautiful piece of curved metal, and it's in a kind of art science display outside CERN. The curved metal you can see in the bottom right, that kind of wiggly spiral thing. Okay, and then you can see behind it, there's a beautiful sphere. Okay, this is not really to do with particle physics, but that's actually made of wood. That was part of the World Expo in Geneva, and the building was donated to CERN. Beautiful building. It's actually wooden. Okay, so that's the periodic table of the quarks, but that's a better picture there. Okay, so yeah, it's a table. It's got columns and rows, just like the chemistry periodic table of atoms have had rows and columns, and just like the periodic table in chemistry. Okay, just like the periodic table in chemistry. The things in the same columns have got similar properties. Okay, so that's pretty much the case as well. All right, and you can see that it's a nice table, sort of 4 rows and sort of 4 + 1 columns. So there's 16 + 1 particles there. And the particle on the top right, the Higgs boson, is the special one. Okay, it is kind of unique. All the other particles kind of have a partner or play a role which other particles play in a similar fashion. But the Higgs boson doesn't. Okay, so it turns out, though, this looks quite messy, but just like the periodic table in chemistry, there are some atoms which are really, really common and really, really important to the Earth, to life, and so on. Things like carbon and oxygen and so on. And the same is true with the periodic table of particle physics. These particles here in the big purple oval are the particles which basically are very common in the universe, the up and the down and the electron. And in fact, the things I've circled there, the up and the down quarks together, when you bind them together into threes, they make protons and neutrons. So they make up the nucleus of the atom, the U and the D quark, up and the down quark. And the electron, of course, is a thing that whizzes around the outside of the nucleus. So those three things circled basically make up atoms. Okay, but they're not just those particles which make up atoms. If you didn't have other particles as well, it wouldn't work. Okay, you need gluons. They bind the quarks together. Without gluons, the up and the down quark would just fly apart, and you wouldn't have stable protons and neutrons. So the gluons glue the up and the down quark together, and the photon plays the same role as a gluon, but that binds the electron together with the up and the down quarks. Okay, so the photon, if you like, is the glue. It's a glue, strictly speaking, for things which carry an electric charge, and the electron does, and the quarks do as well. So you can see, even though it's quite complicated, there's special particles which are really, really important and very, very common in the universe, on the Earth, in our bodies, in rocks, everywhere. Okay, let's talk a bit more about quarks. Okay, how small are quarks? Okay, well, quarks are incredibly small. Okay, so as an example, I'm going to try and explain how small quarks are. Okay, and I warn you, I'm going to fail. Okay, so how small are quarks? Well, if you were to take an A4 piece of paper, and then if you were to cut it in half, and cut it in half again, okay? So here's my A4 piece of paper, and I'm going to cut it in half, okay? So cut it in half once, okay? Cut it in half again, second time, okay? But properly in half, not just roughly like that. If you were to do that 100 times, okay, 100 times, you would get something which is the same size as a quark. That's how small it is. 100 doesn't seem like a big number, but you see how far you can get cutting a piece of paper exactly in half. To put that in some kind of context, let's go the other direction. Okay, imagine taking an A4 piece of paper, okay, and then we're going to double it, okay, and then we're going to double it again, and double it again. It turns out you'd only have to do that procedure of doubling 95 times to get a piece of paper which covered the entire solar system. Okay, so in that sense, a quark is smaller than an A4 piece of paper, then the solar system is bigger than an A4 piece of paper. Okay, so again, normally I'd be doing this live with people in front of me, and so I would then ask the question, does that help explain how small a quark is? Okay, I kind of know the answer to that. So I'd say, you know, has anyone been to Pluto? Does anyone have a sense how far Pluto is? If Pluto was half as far away from the sun, would anyone know? Would you notice it? Do you have a sense for the distance? Of course you don't. The thing is, these distance scales, the large ones and the small ones, are just so far removed from human experience that we have got no kind of gut or intuitive feeling as to their scale. Okay, so how small are quarks? They're incredibly small, too small to kind of comprehend. Kind of that's the answer that I would give. Okay, really small. That's how small they are. And the other amazing thing is that quarks, when they get bound together to make protons and neutrons by the things which we call the gluons, the force which binds them together is unbelievably strong. Okay, so remember how small these things are. You might think the force might be, you know, like a very weak elastic band, or, you know, a million times weaker than that. No, the force is incredibly strong. Okay, it's 15 tons, the weight of 15 tons. Okay, so that's the same as 3 African adult elephants. Okay, that's a lot of force. So that's one of the reasons why it's very difficult to study how the quarks interact, because that force is so strong. You've got to basically include all the effects from different quarks, kind of no matter how far away they are, in a sense. Okay, so that's what we've got with quarks. And because quarks are so amazingly strong, we need to have a special procedure to study them. Okay, so let's think about this. If you wanted to understand how something worked, okay, you would basically take it apart. Okay, so I'm now going to show you an example of that. So here's a bike. Okay. So here's a bike. Okay, yep, it's a folding bike. Now, what are we going to do with this? We're going to try and understand how it works. Okay, we're going to try and take it apart. So what do? Well, imagine you're given some tools. Okay, given a pair of tweezers. Would that be useful to take that bike apart? I don't think so. Imagine you're given an enormous spanner. Okay, this huge spanner, would that be the right size tool to take that bike apart to see how it worked? I don't think so. Imagine though this modestly sized, pleasantly sized, perfectly sized spanner, that's the right size, okay? Sure, okay? So the point is, to take something apart to see how it works, you need a tool of the right scale, okay? So to understand how protons fit together, you need a spanner about the same size as a proton. Now, of course, you can buy one of these from a DIY shop, okay? That's easy. Can you buy a spanner the same size as an atom, okay, to take the atoms apart, or rather the same size as a proton, to take the protons apart? Okay, I don't think so, okay? It's too small. Nature has not provided us with a spanner the size of an atom, or the size of a nucleus, or the size of a proton, or the size of a quark. These things are just too small, okay? We don't have a tool the right size. All we've got, okay, is what's in the periodic table of particle physics. We've got quarks and protons and stuff like that, okay? That's all we've got. So the analogy is for the bike, we've got no spanner, we've just got a bike, okay? We've got many bikes, so it'd be like using a bike, okay? Using a bike to try and break apart a bike so that we could see what's going on. So it'd be like having two bikes, okay, and trying to mangle them together to prise the pieces apart. That's fine, but the thing is, this particular bike, the proton, has got quarks inside, and they are bound together with 15 tons. They're incredibly well built, okay, even better built than this bike, okay? So to prise it apart, you can't just do that with it at low speed. You've got to really fire them hard against each other. Why? Because it's 15 tons you're trying to overcome, okay? It's such a well-built thing, the proton. You've got to fire them apart really, really strongly. So that's what we do in CERN. That's what we do in the Large Hadron Collider, okay? We get protons, okay? And because there's no spanner, the right size to prise apart a proton, we've got to fire the protons head on, like firing two bikes head on, okay? I won't do that demonstration, okay? My bike is too precious to me. Okay, so we've got two protons, we fire them together. Now, just knocking them together like that won't break them apart just as well, because clapping would also kind of break the protons apart and we would all sort of fall apart, okay? These things are very well built, so they have to fire basically incredibly fast. So they've got enough energy so that basically then they can split up. So how fast? Well, basically nearly the speed of light. That's how fast they have to go, okay? And so that's why in CERN, we've got the Large Hadron Collider, which fires things together at incredibly high speed, and they fire head on, and that's enough speed, enough energy to break apart the protons, okay? So let's talk about that some more. And I'll go back to this PowerPoint. So that's what's done in the Large Hadron Collider, okay? So what we've got is a machine, a bit like an old-fashioned TV, Okay, so the TV on the left, very young members of the audience may not have ever seen such a big fat TV. I certainly remember them. Basically, the Large Hadron Collider is a big version of that. Okay, the TV is on the left. What's the thing on the right? Well, that's an aerial photograph above Geneva. And the two circles there, the small one and the large one, are different parts of the Large Hadron Collider. Basically, protons get accelerated in small machines, then they go to medium-sized machines, and then they get injected into the big circle, the big machine. Okay, so they get faster and faster and faster. And as they get faster and faster and faster, they need a bigger machine to contain them, to make them go faster. Okay, so those two circles, if you're in an aircraft flying above Geneva, you wouldn't see those circles. They are drawn on the photograph, representing where those machines exist underneath the surface. Okay, so they're in tunnels. They're just drawn on the photograph so you can see the scale. They're incredibly big. Okay, you can kind of tell by the scale of the photograph, but also if you look on the very, very far right-hand side, you can see two parallel lines. That's the runway of the Geneva International Airport. Okay, these circles, these machines are enormous. But the little tiny TV on the left and the Large Hadron Collider on the right share the same kind of property. They're both particle accelerators. In that old-fashioned TV on the left, it's accelerating electrons. So metal's heated up at the back, and with electric force, okay, they're accelerated away, okay, and they're directed to make lines, and their intensity changes, so you've got a bright spot or no bright spot, which makes up the image. Okay, so that's what's going on with the TV. It is a baby particle accelerator. Okay, the electrons go, and only it's a very small fraction of the speed of light, but nevertheless, it's a particle accelerator. The thing on the right, the Large Hadron Collider, is like the TV on mega steroids. Okay, it's a machine which accelerates protons to unbelievable speed. Okay, how big is the Large Hadron Collider? Well, I'm in Swansea, right in the middle there. Swansea Bay, for those of you who know Swansea, it's a decent size across. From the centre of Swansea around to Mumbles is about 8 kilometres, so about 5 miles or so. The Large Hadron Collider would take up that much space. Okay, for those of you who are not familiar with Swansea but are with London, the Large Hadron Collider has got a length about the same as the circle line, the tube line, the circle line. Okay, it's a much more perfect circle though. Okay, this thing is huge. Okay. When it was being built, it was a huge engineering feat. Okay, they had to dig this tunnel. It is 27 kilometers, okay, nearly 20 miles around. It's massive. Okay, it was a huge tunnel dug, so the engineering feat of doing that was extraordinary. It's about 100 meters underground, and not only did they have to build the tunnel to hold the pipe which they accelerate the protons in, but every now and then they want to collide those protons head on. And that's like colliding the bikes head on to see how the protons are made up, okay, to watch the bits fly out. And so they need to make a larger thing, much larger than the tunnel, like a huge cavern, in which they place their incredibly powerful kind of digital camera. And they are placed exactly in the situation, exactly in the position where the protons collide head on. So the thing on the bottom left is the Atlas camera, Atlas experiment. And that's the photograph taken when it was still being built. Okay, and the things circled in the bottom two photographs, the red ovals, there you can just see human beings. Okay, so that gives you a scale of this. The Atlas Collider on the left is in a cavern which could fit a cathedral inside. And this is a big cavern underground. Okay, and that's the Atlas experiment, the Atlas detector. Pretty much when it's finished, it's just having some service work done on it. Okay, you can't go there when the protons are whizzing around. Okay, and I can't not show a photograph of me at the Atlas detector. Okay, the thing on the right is the kind of vertical tunnel going up to ground level. Okay, this thing is unbelievably big. Okay, unbelievably big, unbelievably powerful. What they do is they end up having two beams of protons firing head on. Each beam, they constrain it So they get as many protons in as small a space as possible to maximize the chance of the collisions happening. The beam is actually finer than a human hair. Okay, so it's basically to hit them head on. It's like firing needles from the UK across the Atlantic, needles from the US across the Atlantic, and getting the needles to hit head on. Okay, it's that kind of chance. So most of the protons miss each other when they go through. It goes at virtually the speed of light. You guessed it, it doesn't go faster than the speed of light, and it doesn't even go at the speed of light. It goes at about jogging speed, less than the speed of light. Okay, 99.999% of the speed of light. Okay, jogging speed less than the speed of light. You think, well, come on, you can go a bit faster. You know, you can easily put that extra speed in, but of course, it's not true. Through relativity, the extra energy required gets more and more and more. Okay, so it goes as fast as it can go, given the technology. Each proton has got the same energy as a blink of an eye. So, you know, imagine your eyelid going up and down. Okay, not very much, but these protons, remember, are tiny. So each proton really, not got a lot of energy by human standards, but by its size, it's got a huge amount of energy. So if you add up all the protons together, it's got the energy of an intercity train. It's a lot of energy. Okay, if something were to go wrong, they direct the beam into a big chunk of copper, and the copper melts. Okay, that's what they have to do to make sure that nothing else goes wrong, no other damage is done. It's been running since on and off since 2012, okay, and very successfully. In order to get the protons to whiz around, this amazing circle through that tunnel in the blue tubes on the right-hand side, they need to use superconducting electromagnets. And they need to cool them down so that the wire carrying the current, which then makes the magnetic force, the wire is so cold that the electricity flows with no resistance. That's a superconductor. In order to do that, they need to cool it down to about 2 degrees above absolute zero. That sounds very cold. Okay, today's an extraordinarily hot day by Swansea standards, but imagine going to like minus 271 Celsius. That's how cold it is. That is incredibly cold because it's actually colder than outer space. So deep space between galaxies, okay, far from anywhere. How cold is it there? Well, it's actually a little bit warmer, not much, but a little bit warmer than inside the Large Hadron Collider. So as far as you know, it's the biggest, coldest thing in the universe. Okay, amazing, amazing. Some of these detectors are heavier than the Eiffel Tower, some of these kind of digital cameras, and they involve these electromagnet wires, and they're incredibly fine filaments. Huge length of them. If you were to stretch them out, it would reach from the Earth to the Sun and back 10 times. Okay, incredible. All the digital there's 4 big digital cameras, 4 big experiments. They take amazingly detailed photographs. Okay, and the amount of, and they take them every time the proton bunch crosses. So they come in bunches, and when they cross, there's a collision, and so many times a second they're taking these photographs. If you work out how much data they're collecting, then it's the same as if every human being on Earth was making 10 simultaneous phone calls. Okay, the amount of data coming out is just extraordinary. So all that data then gets culled down, and only the most important data is stored. Okay, but nevertheless, the amount of data is the same as a stack of CDs 10 kilometers high. Okay, so 1,000 kilometers high. Okay, so that's a huge amount of data. Okay, so who's responsible for it? Well, obviously it's a huge team, but the main man, the guy in charge of it, is a guy called Lynn Evans. And yes, that is Lynn Evans, and he's sitting in, you might recognize the car, it's a DeLorean sports car. Yep, it's a DeLorean sports car. And where was that car? Well, it was in the first Oriole Science venue. Okay, we don't have it still, but it is, it's real. Okay, it's not photoshopped. That venue is just around the corner from where I'm standing. Lynn Evans I'm making a big fuss about because not only is he a great guy, a very kind, gentle, generous person, but he's also a Welshman. Okay, unlike me. Okay, he grew up in Aberdeen, and he did his physics undergraduate and his PhD in the Department of Physics in Swansea University. and he comes back to visit us quite often, in fact. So he's a great guy, and in charge of making that machine, which is about £4 billion worth. Okay, so let's come back to this periodic table. So we said that there's sort of 16 fairly kind of straightforward common ones, which come in partners and pairs or whatever, and they're not kind of unique because, for instance, the up quark and the down quark have got similar properties. But that purple one on the top right, the Higgs boson, was that unique one. That's the 17th one. Okay, that's the odd one out. So what's that all about? Well, basically, the Higgs is named after Peter Higgs, who was basically the first person to propose the existence of the Higgs particle. Okay, so he shared the Nobel Prize about 5 or so years ago, a bit more. Okay, so that's a photograph of a poster again outside CERN. So Peter Higgs is the one on the right, pointing his finger at Anglais, the other guy who got the Nobel Prize. So what we're going to do is we're going to understand how all those things together work, okay? And in particular, how the Higgs works. But before I explain how the Higgs boson works, how the Higgs mechanism works, let's just pause for thought and look at this periodic table of particle physics. Because with a few exceptions, specifically dark matter and dark energy, everything that anyone has ever seen anywhere can be described by this table and the interactions going on in that table. Okay, the Higgs boson was discovered in 2012. Okay, so the Large Hadron Collider was turned on in 2008, and the Higgs boson was discovered in 2012. That was the last piece. It was the missing piece of the jigsaw. And with that piece, then scientists basically can say that they understand everything that they've ever seen apart from dark matter and dark energy. Okay, so everything since the Big Bang, okay, not the Big Bang itself, but everything after the Big Bang, as far as we know, apart from those two things, is described just in terms of that table. Okay, so it is an extraordinary feat that has been achieved. And so now what we're going to do is we're going to try and explain the Higgs boson. Okay, so wish me luck. So I'll get rid of my bike. Okay, and so what we've got here is a bit of rope, okay, and a chain. All right, so I'm in a COVID secure environment, so it is just me here. Okay, so I'm my own camera person as well as the presenter. So what is going on here? Well, I'm going to ask you, first of all, to just concentrate on the rope. Okay, so the rope is an analogy for a particle. So what I'm going to do is I'm going to put this tube on this piece of rope. Now, it turns out that particles start like this rope, horizontal, okay, like this horizontal rope. Okay, so this horizontal rope represents a particle, and this tube can slide along there effortlessly. Okay, so this represents a particle with no mass. So its mass is 0. And why does it represent that? Well, because it's easy to move this along. Okay, if this is going uphill, then like walking uphill, cycling uphill, or whatever, running uphill, it takes a lot of energy. Okay, so it's as if you feel your mass. Okay, so whenever it's curved, whenever it's an uphill part, that represents a particle with mass. Whenever it's horizontal, that represents a particle with no mass. Okay, so what happens then? Well, then what we're going to do is we're going to see how the particles interact. So I have got another rope. Okay, here's one I prepared earlier. And we're going to see how these particles interact. Okay, so there's one rope, and we're actually going to get rid of that. Okay, and there's two particles, okay, two bits of rope, and they're massless. So they're represented by a horizontal thing. And then we've got other particles like gluons and so on, and they bind those particles together, they interact. Okay, so that's just like a clip which holds them together. Okay, so there we have it. They now interact. They're still horizontal. So when one massless particle interacts with another massless particle, nothing changes, they still become horizontal. Okay, now the weird thing though is that there's quantum mechanics going on. Okay, so when they interact, it's not quite that simple. I kind of half lied. So the original particle actually is quantum mechanical, so it's like a guitar string, so it bounces up and down. And you might say, well, hang on, Chris, you just lied. You said that it was flat. Well, yes, on average it's flat. Okay, so on average it's flat, but basically, so on average it's got zero mass. Okay, so that's how a particle is represented. Okay, massless particle, that's how they interact. And the interaction of one particle with another particle, if they're both massless, doesn't change the mass. Okay, great. Now, what have we got here? Okay, so this chain represents the Higgs boson. So it's different to the rope because the Higgs boson is fundamentally different to ordinary particles. Okay, so now the Higgs boson interacts with the particle. Okay, so let's clip this thing on. It's going to be clipped on between the Higgs and this originally massless particle, and look what happens. Okay, the Higgs boson brings it down. Okay, so they still wiggle around because that's quantum mechanics, but on average, absolutely, it is not horizontal. Okay, it is not like that. On average, very much it's wiggling around and it's down there. So the fact that the Higgs boson has got this asymmetry because it's not flat, okay, it bent down, okay, because it's got that asymmetry, when it interacts with a particle, it brings the particle down. Now, what's going on now is the fact that we've got the originally massless particle now has got a valley and a hill. So now imagine walking up that hill, you feel your mass. So the originally massless particle now is given mass by the Higgs boson. So when the Higgs boson interacts with a massless particle, it kind of pulls it down in this analogy. It gives it some slope, which is the same thing in this analogy to giving it mass. So that is how the Higgs boson mechanism works. Okay, so a difficult thing traditionally to describe. Okay, so hopefully I've done that justice. Okay, hopefully Peter Higgs would be pleased at that. Okay, so let's go back to another feature of quarks. I kind of mentioned it briefly. The fact is that quarks are quantum, okay? So quarks are quantum. I represented that with the rope by a wiggle, okay? The wiggle up and down, all right? So it's never in one place, it's always moving around. So the same, the quarks basically have that property. They kind of wiggle around. So unlike a football, if you were to take a football and throw it through the air, it would go from point A to point B and it would go along one single trajectory. Okay, any given time, the football would just be in one place, one position. For things which are quantum mechanical, that is not the case. Okay, things which are quantum mechanical, when you go from A to B, they kind of become fuzzy. Okay, they kind of become blurry, and at any given time, it's a little bit of it somewhere, a little bit somewhere else, a little bit somewhere else again. Okay, so what you say is there's a certain probability that at a given point in time, the particle is at any given place. Okay, so the way to represent that is to say that going from the start to the finish, as you can see in the diagram, this quark can go basically in any kind of path, any trajectory between the start and the finish. Okay, now imagine we're trying to understand this, okay, not just measure quarks in the Large Hadron Collider, but imagine now we're trying to understand this like we were with Aussie Rules Football and trying to understand the rule book. Okay, so we're trying to understand how the quarks move around. Now, we're going to need to, whatever theory we come up with, presumably has to incorporate this incredibly important feature of quantum mechanics. So whatever theory you come up with and the calculations you do to make predictions from that theory are going to have to involve the fact that a quark can go from the start to finish along many different trajectories. So you're going to have to add them all up. You don't just choose the blue trajectory or the green one. You've got to consider the blue, the green, the purple, the yellow, etc. Okay, so that's what you have to do. Okay, so now rather than show a blank screen, we're now going to do a calculation. Okay, so we've got to sum up all the different paths that the quark can take. Okay, so different possibilities is what we're trying to sum up. So what we're going to do now, and this works obviously much better before the pandemic, when I had people in the audience and I could get them to come out. Okay, so what I'd get them to do, I'm going to use these balls to represent two people. Okay, so two people come out. Okay, and we're going to count the number of different possibilities that they can be in, different states they can be in. And the analogy is with a quark, we've got to work out whether it can go from A to B in that direction or A to B in a different direction. So one person, okay, to start with, can either be standing up or kneeling down, okay, standing up or kneeling down, okay? So that one person can be clearly in two different states. Now, I normally bring up a second person, okay, and that person can also be standing up or kneeling down, okay, in two different states. Now, the question is, how many possible states of both of them together? Okay, each is like a quark, okay, each is like a quark, and we're not just studying one quark. When we do particle physics, we're studying many quarks and how they interact. So each can be up or down, and so they can be like that. That's one. They can both be kneeling down. That's two. One can be up. That's three. The other one can be up. That's four. So altogether, there's four. Now I've only got two arms, and because it's COVID safe, I can't bring anyone on to help me. But imagine a fourth one. Okay. Imagine a third one. Okay. The question is, how many combinations can three of them have? Three people standing up or kneeling down. Okay, it turns out it's not six, it turns out it's eight. Why is that? Well, let's think about it. These two can be up or down in four ways. We're now going to kind of throw a blanket over that. Okay, and ignore that and just think that that's four. Okay, there's four ways behind that blanket. Okay, and so now what we're going to do is we're going to take a third one, and that person can be standing up, and this can be in four ways, that's four, or she can be kneeling down. So it's kneeling down plus those four. So it's four plus another four. So it's 2 times 4. So they can see the pattern. Each time you have a new person, it's twice as many combinations as the previous number. So it went from 4 to 8. We went from 2 to 4. Okay, so that's what's going on. So very, very quickly, you get to a large number because it goes 2, 4, 8, 16, and so on. Now, particle physics involves many, many particles. So many, many quarks. Okay, the analogy is many, many people. Now, let's take the Swansea Liberty Stadium. It's about 20,000 people there. Okay, 20,000 people there. Okay, now imagine this thought experiment. At halftime, okay, maybe the Swans are playing or the Ospreys are playing. Okay, halftime, I walk on and with a microphone, I say, okay, everyone, we're going to do this experiment. Bear with me. Okay, as if that's going to happen. All right, I'm going to get every person to stand up or down. We're going to count how many ways there are. How many ways do you think there are of 20,000 people standing up or sitting down? Okay, how many ways do you think? And obviously it's a large number. How large a number do you think it is, say, compared to, I don't know, the age of the universe in seconds since the Big Bang? Okay, think about the number of different ways and think about how old the universe must be in seconds. Which do you think is larger? Okay, so that's a tricky question, okay? And I am now going to show you how that works. And here is the answer. So the number of ways that Liberty Stadium people can be standing up or kneeling down, okay, if there's 20,000 of them, is this many, but it doesn't finish there. Doesn't finish there. It's a very large number. Doesn't finish there. Doesn't finish there. It finishes there. Okay, that's how many ways. So it's 2 times 2 times 2, but 20,000 of them. So it's 2 to the 20,000. Now, that's the answer to the question, how old is the universe in seconds? So it's 400 million billion seconds. Okay, it's about 10 to the 17, 10 to the 18. Okay, really tiny compared to how many ways it is that 20,000 people can be either standing up or kneeling down. Okay, so very, very quickly, just with 20,000 people and counting different possibilities, you can get to numbers which are huge, huge compared to the age of the universe. Why is this important? Well, remember that what we're trying to do is we're trying to think of the theory, devise the theory which describes how quarks interact. But because they're quantum mechanical, when we do calculations from that theory, we've got to calculate and include all the different possibilities. And with a small number of quarks, the number of possibilities becomes very, very quickly really, really large. So we've got to do this mind-numbingly difficult calculation, which involves many, many paths of the quarks. How on earth do we do that? Well, we use clever technology, clever mathematics, and very, very powerful computers. So some of the most powerful computers on the planet are being used right now to study how the quarks interact. In fact, this is my research area. Okay, so there's a photograph, not of just black boxes, but those boxes contain, by the looks of them, blue gene IBM computers. Okay, and there is a very gender neutral photograph of 2 people in front. Okay, so we use supercomputers. So that's what we do. Okay, so where does this leave us? Well, I started up by talking about sport. I started talking about Aussie rules football, and I asked you to imagine that you're trying to derive the rule book of Aussie rules football. And I did the analogy that doing that is like being a particle physicist, because a particle physicist basically tries to derive not the rule book of a sport, but the rule book of Mother Nature herself. Okay, so just as you know, with Formula One going on now, the Tour de France finishing, perhaps it has already, I'm not sure, perhaps quite soon, with the Euros, football, soccer, we won't talk about that, with the Olympics starting very, very soon, all these amazing sports people out there doing their thing after huge amount of training, all right? Difficult to imagine that you could ever be like that good at that sport, but we can all be sports fans, okay? We can all think, yeah, I follow the sport, I dabble in it a bit, I like to watch it on TV, I like to understand it, okay? Just as the same with the sport, we can do the same with science, okay? So we can be a science fan as well. We can dabble in science, we can show interest in science, and we can study science, okay? So that's what being a particle physicist is like, okay? And that's what also like being a science sort of fan. So we can all be sports fans and all be science fans as well. Okay, and so that is where I'll leave it. Thank you very much for your attention.